Welcome to the AP Physics Workbook tutorial. Here we have Unit 4 for Work and Energy. The section is 4.M, Energy and Projectile Motions. Right here, I give you the projectile motion equations in case you need them. You could read the scenario to yourself and try to make sense of it. It's a little bit more complicated than it is, so I want to be trying to simplify. Where this question comes from is an old problem from like Tarzan trying to swing on a rope. Right? And notice that there's going to be a height. All right? And then that height is going to be based on the rope that he has. That's exactly what this scenario is. Then notice that at the start, the rope is supposed to be completely horizontal. So it's supposed to be, in theory, looks like this. Right? Then as he swings, it's going to go like this. Okay? And that length stays the same. So if this is the height, do you see how this is the height? Then has to be the height. So if this is super small, this is going to be super small. If this is super long, this is going to be super long. So therefore, when it swings, it's going to be super long. Okay? That's exactly what this question is asking. All right? So let's answer the first one. Why does the person land in the moat if the length is very short? All right, so let's just take a look. If this is super short, do you see how it's super short? So he's going to swing and he still is going to fall down like this. Okay, it's going to be here. He swings. You see, too short. He's going to fall down. Right? Here's the explanation. Short rope means short rope means small gravitational potential energy because U equals to mgh. Small gravitational potential means small kinetic energy because gravitational will equal kinetic during the conversion. Small kinetic energy means small velocity because kinetic energy is 1/2 mv squared. Small velocity means it can only travel a small distance. Look at the kinematics equation. So the distance can be seen as x minus x naught. Substitute that in. You would see that it becomes x minus x naught plus v x naught t. We saw that d can be written as the velocity times the time. So there you go. This shows that it will only travel a short distance if the velocity is small. And here's the reason why. The example would be here. Notice that this is super small, right? So it swings super small. So it's going to have a small velocity, so it's not going to go that far. Why does the person land in the moat even if the rope length is nearly the same height as the platform? So this is saying this is super long, right? So it's going to swing super long. So the person should go super far. All right, let's see the math. Well, it's going to be the same equation as before. The distance traveled is going to be based on the velocity in the x direction, naught times time. You see here the rope is long. The fact that the rope is long, there's going to be a large h. That means there's high gravitational potential because U equals to mgh. The high gravitational potential will convert to high kinetic energy. The high kinetic energy means there's high velocity because kinetic energy is 1/2 mv squared. The high velocity means the object can travel super far. However, by the time the person lets go of the rope, they are already on the ground because the time is extremely short. So let's take a look. How that should look like is this. Here you go, super long, he swings. By the time it comes to the ground, right, and the person let goes, okay, you see how they're super close to the ground already? Same thing here. Super long, he swings, he has a lot of energy, but by the time he hits it, look, he's already near the ground. So he can't go anywhere. So he's just still going to fall in the moat. Right? If it's too short, right, he falls in the moat If it's too long, he still falls in the moat. Why? Let's take a look at the math. We would see that the horizontal speed at the moment they let go would be, well, it's all potential, so U will be equal to the K at that point. So the potential in the rope is from the height, which is just mgh, but we know that h in this case is L. Remember, h is going to be equal to L. So here you can write this as mgl is going to be equal to 1/2 mv squared. If you solve for v, it should look like, let's see, gl equals to 1/2 v squared, right? The mass cancels. 2 goes here. That's how you get rid of the 1/2. Then you square both sides. Okay. And that's how you get the v by itself. So v equals to the square root 2gl. Let's solve for the distance. Say y will be equal to h minus l, which is going to be equal to 1/2 gt squared. Right? So if we solve for that, t will be equal to 2h minus l over g. This is basically the length right here. Right? So whatever, so here, let me show you. When this swings, right, it's going to be, do I have a rotate function? Yeah. Boom. You see? You see how it rotates? Okay. So this distance here is going to be h minus l. All right? That's how I'm getting h minus l there. That's really the length of it. All right, so describe how your equation from part 1 and part 2 supports your reasoning. I would say that if the length of the rope of L is extremely small, like 0.001, then the velocity is also small because they have a direct relationship like this. So L goes super small. Right, this becomes super small. Okay, this goes super small. Right, this is small now. Then when you take the square root of a small number, you get a more. Right, square root of a small number is gonna get you a more, right, an extremely small number. So that proves why that you will have a low velocity if you have a small length. All right. Okay. Because L has a direct relationship with V. Well, a squared relationship. So if L is, let's say, 2 or 4, velocity is 2, right? You take the square root of L, gets you V, right? Ignore 2g because we're comparing it, right? Describe how your equation from part B1 will support your reasoning here. Well, for that one, I have the answer right here. All right, so let's take a look. Now let's grab this equation here, bring it down. So if L is equal to h, then h minus L will go to 0. So this will go to 0. Well, it's technically not going to go to 0. It's going to become a super small number, right? Notice that HL is actually in the numerator. So this is how I looked at it. So I took out the square root and still put a 2 here. Okay? So I didn't look at the square root. I looked at the square term, right? And notice, which means that HL is in the numerator, which is on top, and it goes to 0. If that goes to 0, T will also go to 0 much quicker because it's squared, which means that as time will decrease, as height gets closer to L. Right? So HL is the difference between the height and the length of the rope. If that difference between them goes to 0, that means, what I mean by that is, do you see this L? It's going to go, right? It becomes H. When these two become the same, that means this goes to 0. As this goes to 0, T will also go to 0 because, again, it's in the numerator. It has a direct squared relationship because of the squared there. All right, there you go. That's everything that you need for 4M.